The subject of this session is meaning. Now, you may be aware of a book that came out, 30 years ago, called The Meaning of Meaning. But I never felt that this really got anywhere. To say the meaning of meaning is to invoke the circularity of all definition. If we want to really get to the nature of meaning, we have to get some other reference. And when I first stumbled on the idea that meaning was angle, I was quite encouraged by the fact that I found that the Egyptians had said this thousands of years ago. All meaning is an angle. Now this can be brought out. For instance, suppose we state, well, my opinion is diametrically opposite yours. When I say that, I invoke a geometrical concept, the diameter. 2 points are diametrically opposed. Or we can even carry this out. We think of two contestants, such as in a tennis game or even in a court case. The two contestants represent an opposition. Now the judge takes a position that's not halfway between, because that would be nothing. He takes mediating. He has the power of judgment. So it's a different power from what the contestants have, and it can be represented as a right angle. And if that right angle is leaning over toward one side, then the judgment would not be fair. Well, then we could ask, what is a just judgment? We look up the word just, and it says right. A right just judgment is a right judgment. Well, what is a right judgment? And you look that up and you find it's a just judgment. But if you jump over into geometry, the word right also means a right angle. So we can converge on our subject by saying that which judges the opposition, that which mediates the opposition, in order for it to be right, it must lean neither to one side nor the other. It must be exactly perpendicular. This leads to the title Geometry of Meaning, because by recognizing that there are, for any dichotomy, there is another dichotomy that cuts across it at right angles and mediates it, we also invoke the concept of a right angle and hence of angles and geometry. This is the basis of the book that I've entitled The Geometry of Meaning. To get into this subject, we can start with the problem of the knower and the known. And I have a simplified diagram here which depicts the knower as an eye and the known in this case as a triangle. Now, there are different kinds of knowledge that we can draw immediately from this diagram. First of all, the knower, represented by the eye, looking at a triangle. What is a triangle? A triangle is an equilateral triangle with three equal lines joined, or 3 points joined by lines. The definition of a triangle is self-contained. It doesn't matter whether the triangle is near the person or far away, or whether the person likes the triangle. The definition of a triangle stands. It can be stated and formulated, 3 lines or 3 points joining one another. Now, On the other hand, there are other relations or relationships that the knower can have to the triangle. He may say, well, I don't like triangles, or triangles remind me of the eternal triangle marriage condition, husband, wife, and lover, or that triangle. It's interesting to extend all these things that are not contained in the triangle. In other words, I like the triangle, the one I first mentioned, but you could also talk about the size of the triangle. Because if the triangle is very close to the eye, or if it's very far away, this difference is how big is the triangle. Well, the bigness of the triangle is not an objective factor. It's something that has to be related ultimately to the self. See, if you were alone in the universe, you couldn't say how big you were. You have to have some other comparison object. Now, this relation to the triangle that the self projects on the triangle, which includes liking and disliking, but also scale, is what I call projective, as distinct from the objective relations of the triangle to itself. On the other hand, there's another set of relationships which proceed from the triangle to the knower. In other words, you could say, well, that's not a perfect triangle. There's a little bend there, or there's a dot there, so it's not perfect, or I measured the sides and they're not exactly equal. These are data which the object conveys to the knower. They are objective data as against the projective which the knower, so to speak, invests in the image. Now that gives us three categories. The relationships that are self-contained, that is, of the triangle to itself, the relation of the knower to the triangle, that is, projected by the knower on the triangle, and the relations that the triangle conveys to the knower. These are objective because they're coming from the object. Is there any other category? You see, we have the triangle to itself, the knower to the triangle to the knower. Well, there must be a fourth category, which is the relation of the knower to himself. That doesn't make any sense, but when you think of it applying to the triangle, then it is the relation that the knower creates for the triangle. In other words, what purpose does he use it for? You might use it as an emblem, you might use it as a geometrical proof, you might use it as the thing you hit in the orchestra that makes a noise. What is the purpose of the triangle is something that is completely separate from the object. See, for instance, while making these charts, I used a clock to draw a circle. Now, there's nothing in the clock that says this, I am a compass. The clock didn't contain the purpose. It was I that used the clock for the purpose. This fourth category then becomes the purpose for which you use the object. It is still a relationship and it is still connected with the object, although it is not an objective property. It's a projective property. Now, we had already a projective property in that the knower said he didn't like triangles. So we've got two projective properties. We also have two objective properties. The self-contained relations of the triangle and the data that the triangle as object conveys to the knower. Those are both objective. So we need another distinction. We need to separate the two kinds of projective and the two kinds of object. And fortunately, that's possible with a single distinction. When Noah says, "I don't like triangles," he's making a generality. On the other hand, if he proposes to use the triangle as an emblem for the Phi Beta Kappa or whatever it is, the Triangle Club, this purpose is particular, whereas his dislike of triangles may be general. In a similar fashion, the objective properties of triangles are general. That's why you can define a triangle, or why the word triangle covers a great number of configurations of triangular shape. But when I said this one has a bend in this side, or a little mark there, that's a particular. So there are objective particulars about this triangle and general. Wait a sec, now I'm getting mixed up. Both of these are objective, but the particular objective is what comes from this particular triangle that's been drawn here. The general objective is the definition of the triangle itself. So that makes it possible to think of two dichotomies. So we began with the dichotomy of knower and known, projective and subjective, but we further distinguish with particular and general. And if we make those two dichotomies at right angles to one another, we're launched on our geometry of meaning. Now, these are the four kinds of relationship, and they have many, many, many exemplifications. One that's perhaps the most well-known is Aristotle's four causes. If you recall, the Aristotelian causes were the material cause, the formal cause, the efficient cause, and the final cause. You'll have to just keep them in mind and try to assign them to those four kinds of relationship. Think, for instance, of the formal cause. That means the form. The form of the triangle is its definition, its shape. You might call it the blueprint of the triangle. Generally, the four causes are related to a table, in which case the formal cause would be the blueprint of the table. And if we continue with the table, the material cause would be the wood that went to make up the table. The efficient cause would be the carpenter making the table, using the blueprint and using the wood, but he forms the wood according to the blueprint and thereby combines the formal cause and the material cause into the efficient cause. Well, what's the final cause? The final cause is what brings the table into being. That's why it's called final, namely the purpose of the table, which would be something to put things on. We can play around with this, and I'm going to be coming back to it. Maybe I better make a few more examples. In the book I use an elephant. Of course, the textbook will define the elephant as a mammal of such and such a family and genera, the proboscis, is a definition. It would apply to any elephant. That you might go out in the jungle or go to the zoo and then you meet a particular elephant and you are surprised how hairy he is. You hadn't, definition hadn't said anything about hairiness. Or you might be impressed with the warm breath blowing through the trunk. These are sense data which you get from the actual object. On the other hand, you might have, let's say, convictions about elephants that they were ferocious beasts. And then you might actually find an elephant and find that he was very gentle. In other words, it wasn't true. Well, that's often characteristic of these projections. They're based on some previous memory or even some false data, so that you project qualities onto objects that they don't actually possess. Now, when we come to the purpose or final cause of the elephant, well, what are we going to do with an elephant? We might use him in a circus, or we might use him as a mascot for the Republican Party, or we might use him as a beast of burden, or as a subject for biological studies. There are a whole variety of purposes of the elephant, and that would be entirely up to us. There are other delightful examples. I'll leave one for you to think about and then pass on. What are the four aspects of a map? In other words, given a map, what else would you need to know if you were lost? I won't try to cover that, but it's something to think about. Now, as I said, these are four types of relationship. But we can also find that there are other things beside relationship. For instance, there are actual actions, or let's just call them actions, in which case you're doing something. And to illustrate this, I can show it with a pendulum. Here I've made a pendulum, and I can swing the pendulum. Now, in order to completely analyze this swinging pendulum, we have to go through a certain mathematical procedure, so forgive me. But you notice it swings from side to side. And it also, the speed is varying. Now let's try to analyze that. Suppose I adopt the convention that this is positive. That's a positive position to my right. This will be a negative position. Now, if I let go in the positive position, it swings back, reaches the negative position, and then comes forward again. Now, while it's going at the positive position, its velocity is 0. And at the negative position, the velocity is 0. In between, the velocity is a maximum. Now, there's another factor here, acceleration. Acceleration is the rate at which the velocity is changing. And if we can note, first of all, that when the position is positive, that's here to my right, the acceleration is negative because it's trying to go back. And we can also recognize that on the first half of the swing, if we call this velocity negative, when it comes back the other way, the velocity will be the reverse of that, so it'll have to be positive. So it's going from a positive position to a negative position, from a negative velocity to a positive velocity, from a negative acceleration, and there would be a positive acceleration over here. Now, the way to show this on a diagram is to represent these three categories that I've described which are technically represented by L for position. See, now this was my extreme right, so the diagram is backwards for you. At any rate, this would be where I started, where the position is positive. This would be the swinging through velocity. Velocity is position divided by time. This would be the negative of the position, but it's where the acceleration, which is L divided by t squared, where the acceleration is positive. Now you can think of the pendulum as swinging between those two extremes, going from positive position to negative position, from negative acceleration to positive acceleration. In other words, acceleration and position are diametrically opposite. See, position, acceleration, diametrically opposite. Velocity is represented as right angles to the two. Now, we could say, well, this is the negative velocity. But since the negative position has a positive meaning as acceleration, we might ask, what is the positive meaning of the negative velocity? In other words, what's this up here? Now, watch what I do. I accelerate and decelerate. I control. I can control the thing by moving this with itself. I can control the whole operation from what would be this fourth point. I give this point the meaning or the name control. I hope you can read it. It says length divided by t cubed. Now let me see, I know people get into paralysis when they see a formula, but this is a very simple thing and it's been enormously productive. If we go back into Greek times, there's a story about Zeno. Zeno proposed the proposition that the arrow couldn't possibly be moving because at every moment it's at rest. And no matter how many moments you add up, you won't get movement. In another form, the Zeno paradox took the example of a race between Achilles and the tortoise. The tortoise had a head start, and Achilles, said Zeno, could never catch the tortoise because in the first instant he'd be getting to where the tortoise was, in the next instant, during which time the tortoise would have moved ahead. Let's say this is Achilles and this is the tortoise. So Achilles moves to here. Meanwhile, the tortoise has moved to here. Well, when Achilles gets to here, the tortoise has moved to here. And when he gets to here, he moves to here. So Zeno said Achilles could never catch the tortoise. Well, it's ridiculous, but the point is that the rational mind can't cope with that. It wasn't until Newton invented the calculus that you had a formal description which would get past this so-called paradox. Newton invented the formula for velocity. Seems very simple to us now. We talk about velocity all the time with all these cars and missiles and things. But just the concept of taking length or position and dividing it by time, that's what velocity is. Miles, that's a distance per hour, or feet per second. The per means it's divided by. So velocity is distance per time. And at the time that he introduced this concept, Bishop Berkeley, who was otherwise a very intelligent person, said this was absurd. Of course, Newton had to talk about very small increments in order to talk about the rate of change on a curve, And Berkeley said that was ridiculous because the ratio of infinitesimals was doubly impossible. The infinitesimal was possible and it's impossible anyway, and the ratio of infinitesimals was still more impossible. Well, that's not right. It's a matter of getting used to it, but people now accept that a ratio of infinitesimals can reach a limit, and that limit is the velocity of that object at a point. Now, I'm going into this detail to encourage you to stay with me on the formulas, because it was the formula that got past the paradox. Newton also talked about the rate at which the velocity changes. Suppose you say, well, my Volkswagen can accelerate to 60 miles an hour in 10 seconds. That would be pretty good for a Volkswagen, but let's assume. You notice that I've said time twice. I've said per, it goes 60 miles per hour per 10 seconds. In other words, I've divided by time twice. That's what the t square under the L means there. Now, for some reason, well, for very definite reasons, really, but until they were enunciated, there was no reason, Newton didn't carry it any further. I'm talking about the possibility of taking one more derivative and saying, what is the change of acceleration? Now, it's such an obvious thing, and everybody's doing it all the time, because how else do you drive a car? It's only by changing the acceleration that you can control the car. You put on the brakes, or you push the accelerator. And even steering is a form of changing the acceleration, because you're changing the direction of velocity, and that means a change in velocity, and change in velocity is acceleration. Now, this is much the way much like many of the human predicaments. We do these things instinctively, but the difficulty of stating it in formal language, making it part of our know-how, is quite another step. We know how to walk, run, so on, long before we had the formal equations for speaking of velocity, acceleration, and control. Now, why was it that Newton left out the control of acceleration, this fourth one? I really don't know whether he knew about it or not. But the reason science leaves it out is because science deals with the closed system. See, when you're pushing the accelerator, you're feeding new energy into the car, and that is what changes its speed. You're changing the rules, so to speak. You're interfering with the closed system of let's say the billiard ball, the machine, what have you. You're doing something from the outside. And naturally, there would be no point in having machines if you couldn't control them. But for some reason, for the reasons of giving the rational mind what it wanted, the rational mind wants to explain everything. So science was insistent that in order to explain things, you mustn't interfere with it. You must let it alone. That was fine, but in the process of letting it alone, they forgot that that leaves man out of it. So now they want to go a step further and say there is no man in it. We've got all these laws worked out, and we can't have someone stepping in and changing them. Well, that's getting the cart before the horse, because the reason the laws are worked out is so that you can step in and use them. Otherwise, why make the machine at all? This is such an obvious point that I feel a little embarrassed talking about it, and yet I've never been able to convince a physicist that this is a valid step beyond the acceleration that he knows about. Now, the term, this factor is recognized in aviation. It's called jerk. But that designation is largely because black box is used in a control system, and it has to be either on or off. So it results in essentially jerk. Whereas when you drive a car, you can apply the brake smoothly, or you can apply the acceleration smoothly. It doesn't need to be a jerk. Now, if this system is correct, in other words, this ratioing that I'm doing, which is equivalent to taking the derivative. This is the first derivative, the second derivative, the third derivative. Well, then we should be able to come around here and get back to where we started. In other words, the fourth derivative should be position. Well, then we have to ask ourselves, well, what is it that controls the control? I ask this in seminar, and I'm surprised how few people can answer it. You get in your car and you drive, and you keep on driving, steering, etc., etc. What is the fact, what is the thing that controls the way you control the car? Well, when you get to your destination, you put on the brakes and stop the car and get out. Now, what is destination in terms of these, what I will now call measure formula, because that's their name in physics? Destination is a position. In other words, it's not the same position you started, but it's the same category. The destination isn't a velocity, it isn't an acceleration, it isn't a control, it's a position. Similarly, if you had a remote control missile or a target-seeking missile, see, the missile the missile is just shooting through the air, but you have a control device on it so that the target is sensed. It picks up some kind of image of the target and tries to home in on it. If it's going too high, it'll come down, or too low, it'll go up. It homes in on the target. The target is, again, a position in space. So this is a very important step. We've shown that the derivative, that is this business of going from position to velocity to acceleration to control, takes us back to position in 4 steps. It is therefore what's known as a 4 operator. A 4 operator means something that returns to the start in 4 steps. It doesn't mean that there aren't higher derivatives, but the higher derivatives fall on these categories again. For instance, suppose this guided missile that I was talking about was an airplane, and the airplane is trying to get to this target. Now suppose I'm trying to intercept this airplane with another airplane, and I come along and say, well, he's going to that target, I'll go there, I'll get there, I'll shoot toward there and be able to intercept him, gun him down before he gets there. Well, then we get into a new ball game, because we get to the fact that the pilot of the other airplane may anticipate my trying to intercept him, so he will pretend that the target is here when it's really over there. A similar thing would happen to a boxer. A boxer feints. He makes as if to hit with the right to the jaw and instead hits with the left to the stomach or something. But you still are using this diagram. If the factor of deception is involved, then you have to go around again. Well, what have we been talking about? These are the four kinds of action. The four kinds of action are related to the four kinds of relationship, but they're two whole separate families. And I want to show how that kind of relation can be distinguished from the kind of relation I've been making between the members of the fourfold, that is, the different angles. Here I have a diagram, a list of words and the formulas that were mentioned in this diagram. These see, here we have L over T, L over T squared, and L over T cubed. I'm going to put them over here for a reason you'll soon see. Those are the four actions. Now, what I'm talking about in physics would be called the measure formula, and these are sort of the fundamental ones. But there are other measure formula, and there's a new set I can get to by multiplying each of these by mass. Perhaps the most familiar one is the third. If I take acceleration and multiply by mass, I get force. Now see, on the Earth's surface where we are, there is the acceleration of gravity. But you're not aware, you're only aware of that acceleration of gravity through forces. The force comes about because of the weight. For instance, I lift a light object and compare that with lifting a heavy object, the difference would be the mass. But the gravitation at the Earth's surface hasn't changed. The force has. So force is mass times acceleration. In a similar fashion, velocity. Velocity, when multiplied by mass, creates momentum. Thus we can speak of the momentum of a car hitting a telegraph pole. If a feather had hit the telegraph pole at 60 miles an hour, it wouldn't have damaged the telegraph pole. But if a 2-ton truck hits the telegraph pole at 60 miles an hour, there won't be much telegraph pole left. The momentum, in other words, is proportional to the mass of the truck. Now, this is a little more abstract. This is length, of course, but suppose I have a lever. I want to pry up a stone. So I have a crowbar, and I shove the crowbar into the stone. That doesn't lift the stone. I have to put my weight at the end of the crowbar and push it down to have enough moment, leverage. Moment is leverage. It's mass times distance. Now, if I couldn't lift the stone I remember last summer we're trying to get the roots from a tree that had fallen down, and even with a crowbar I couldn't lift the roots. So, and my weight, I couldn't increase my weight. So I went and got a longer, not a crowbar, but I got a 20-foot beam, 3 by 8. And using that beam, putting a chain around the rope and around the beam and a pivot, then when I stood on the end of the 20-foot beam, I could lift the root right out. In other words, moment depends on mass. The mass in that case was my weight, times the length either of the crowbar or the 20-foot beam. So you see how these things mean something different when multiplied by mass. This is the only one that's not referred to in the textbooks. You remember, control was not referred to in the textbook. But when you multiply mass times control, you get this one that I call mass control. I think it has a name in aerodynamics. It's called power control, but that's not really correct. It's either force control or mass control. In any case, the formula is ml over t cubed. And that's the beauty of these formulas. It doesn't matter what name they have. The meaning comes from the ingredients in the formula. And that's why it's possible to have the science of moving bodies. Often these formulae get mixed up, especially people who are trying to invent things. They get force, power, and things like that mixed up. For example, how is it possible for a 100 horsepower automobile to be stuck in the ditch and along comes one horse and pulls it out? See, it isn't a question of horsepower, it's a question of force. And one horse can exert more force than a 100 horsepower automobile because the force is being exercised or being exerted at a much slower rate. So the force can be greater for the same expenditure of energy. Speaking of energy, you see that's not present in this list. Well, energy is on a third list that I want to show you here. We don't have the word energy, but we have work, which is the same thing. Preference for work was because it's a shorter word. Does that show okay now? Work. In other words, if what's the difference between this one and this one? See, it's L squared. If I exert force for a distance, I get work. If I go upstairs, let's say 10 feet, and I weigh 150 pounds, then I've done 150 foot-pounds of work. Now, the next step from work is to talk about how fast can I do this. In other words, I divide by time, just as I did to get velocity, the rate of doing work. If I go up 10 feet of stairs in 1 second and I weigh 150 pounds, how much horsepower is that? It's 150 foot-pounds per second. 150 pounds, times 10 feet. 150 be 1,500 foot-pounds in 1 second. that is about 3 horsepower. That it wouldn't be possible for me to get up 10 feet of stairs in 1 second. I can say that categorically because the maximum a person can exert is, over any length of time, is about 1/4 of a horsepower. Maximum would be 3/8 of a horsepower. All of this was very important for this person who tried to fly across, or who did fly across the English Channel under his own power. He had to get such an enormous span of wing and have it so light and had to stay so close to the ground that the 1/4 horsepower that he could exert was enough to keep him afloat. Well, I didn't really give you the whole picture here, but what's happened is I've multiplied each of these by L and got a new set. From moment, I went to moment of inertia. From momentum, I went to this action. I'll be talking a lot about action. From force, I went to energy or work. And from mass control, I went to power. Now, power is well recognized and this formula will be found in all the physics books. So this verifies the legitimacy of these because they, like power, are third derivatives. So you can't rule out the third derivative on the grounds it's not in the books because this is a third derivative and it is in the books.